Well, it's official. We can get started. Welcome back, everyone. We're now on week 3 of 16. It's kind of going slow for me, but at some point it feels like it goes really fast. Any questions at all, folks, coming back from our long holiday? Okay, well, I've got a good amount of announcements here I want to get through. So first, we're here in section 2.4, and the major announcement is that means we're now at the last part, the last section that's going to appear on our first exam. Our exam number 1 will be held on September 11th. But this is a kind of an unusual class. First of all, it's fully online, synchronous online. So when we say we're holding it on September 11th, it doesn't mean we're all doing it necessarily at the same time or in the same location. In fact, we won't have a class at all next Wednesday. So all we'll be doing is completing our exams. Some folks will be testing at the Pocatello Testing Center. Others are at the Idaho Falls Testing Center. And I sent your ISU email account directions for scheduling your exam at the correct testing center. Any questions at all, folks, about those emails or how to proceed with the next steps? Okay, my recommendation is try to get the exam scheduled as soon as possible, just for the sake of flexibility. The reality of, say, the Pocatello Testing Center, just as an example, is that it is a pretty busy testing center, and sometimes the testing center itself can fill up at certain time slots. So it's more of a first come, first serve when it comes to scheduling those kinds of things. So if you have kind of a problem on Wednesday, say after 4 o'clock, be sure to call them sooner so you can get it scheduled a little bit earlier. You can schedule it for 2 o'clock, the actual time the class is scheduled to meet on that day, but it can be scheduled for any time of the day. And if something weird happens where seats just totally run out on Wednesday, you can schedule your exam for a different day of the week, and that would be all right. Some people might want to do it earlier on Tuesday. I'd say that's not recommended unless you have to leave town and there's nothing else you can do about it. Other people might have to make Thursday work or a Friday, and that would be just fine. So that's pretty much how scheduling the exams will go. And on with the next bit of announcements. Because we're coming up to our next exam, we have the information that'll be for the coverage on this exam, just those sections in particular. It's closed book and closed notes, but you definitely want to bring a calculator. It's just going to be these two calculator models that are allowed on exam, so no graphing calculators. Pretty much the same ones that you've been using all class. These two that we mentioned in the syllabus is the one you'd want to bring. So that's all it's going to be going on with this exam, just those sections. You'll have a calculator, and even though it's closed book, closed notes, this is the actual last page of the exam. That's not something you have to print out, but when you're studying for the first exam, you ought to have that file available just so you know what's actually included. You don't have to memorize verbatim, and that will help you direct you on your studying. So this will be the very last page of the real exam. Again, you don't have to print this out. This will be attached, and you can just reference it as you're solving the exam. And what we'll have is the limit laws that we're seeing in the current notes, section 2.4. It's essentially the same limit laws all the way in section 2.2. Only difference is we're going to a finite number A instead of infinity. But essentially, all of these probably look just about exactly the same to you, other than that small little change. So these formulas do double duty for section 2.4 and 2.2. That's kind of nice. And other materials you'd want to take a look at are just the sample exam problems. I have 2 versions here to give you a feel for what kind of problems you should be prepared for on the real exam. Any questions so far? Okay, well, let's take a look at these just because it's our first time doing this kind of thing. These are pretty long documents, so if you open up version 1, here's what it looks like. It's on a section-by-section basis, just the routine problems that you should be familiar with. So you can think of this as a study guide, essentially, or a worksheet that you can complete and work on. As you go through here, you'll see the typical problems that we did in class. And at the very end of the document are solutions as well. So you can use this to check your understanding, see where you're at. If anything seems weird about these solutions, these were hand typed, sometimes drawn by me, and typos do happen. Don't hesitate to email. I can clarify how I got the answer, or maybe just fix the typo or mistake I might have made. I try to avoid those, but that's the reality. Mistakes sometimes happen when you're typing up so much stuff. So this one is essentially kind of like a rehash of these lecture notes, new problems, new things to practice. For version 2, this one doesn't look like it's super useful when you open it up, but it's just as useful. Some people might think that version 2 is better for them. Other people might prefer version 1. It's really kind of up to which ones seem better when you're studying these. But this is all that's going on in that document. It seems kind of vague at first. It says section 2.2, check out these exercises, and same with the other sections. So how would you do that? Well, don't forget, for this WebAssign system we're using, you do have a book, and it's right here, my ebooks right here. If you click on that link, click on it again to actually open up the book. Then let's see, take another look at our information here. It says go to section 2.2, page 109. The page number is not as relevant for the online book, but I figured might as well say what it is. I would go to section 2.2. So here is section 2. It's weird having your book load. Here's the 2.2 section exercises. If it didn't take you directly there, click on this little expanded menu bar, and you can scroll down to the 2.2 exercises in that way. And this notes back here says, take a look at exercise 5, 9, 11. So here's exercise 5. What I would do is just copy that down on paper, write out that limit, whichever steps you need to take to show what would happen. Then click on here after you're done and see if your answers are matching up with what you see here. So I try to assign just the odd problems. Let's see how close I got with that. It looks like almost entirely odd problems. There may occasionally be an even problem just because it might be just a really good exercise I couldn't leave out. If that happens, I'll try to provide the solution myself on that document. So that's how the second version of the sample exam goes. Any questions at all, folks, with that second version, or any questions in general? Okay, so version 1 is exercises that I just did again. Think of it as a second version of the lecture notes. These come directly out of the text. And as you're doing these problems, again, you'd probably want to refer to this, not just because it's a list of what's actually provided on the exam for formulas, but it's also more, when you go to take the real exam, this is just a lot of stuff. It's kind of overwhelming, if I'm honest. But if you study with that thing pulled up right there, you'll know where all the relevant information is, and you'll find you're spending far less time in a real exam setting just looking stuff up. You know where the formulas are. You might even find that you may not even refer to this because you became so familiar with it over the course of studying. So that's the new thing that happened this week for the materials here. That means our goal for today's class, and when we come back next week on Monday's class, the 9th, we're going to finish off section 2.4. After 2.4 is finished, I'll take any review questions that folks might have over these sections right here. So it'll turn into kind of an impromptu, informal review day after we finish 2.4. If we run out of questions, we might go to the next section, 2.5, but that's pretty much how our schedule is going to be at this moment. Just finish off 2.4 and start taking review questions. Well, any questions or comments at all, folks, about any of those ideas at the moment? Okay, that's like 9 minutes of announcements already, just about. I have just a little bit more, and then we'll get started on that last section, 2.4. I think I can close that out. My last announcement is more just some other interesting things you can do inside here in WebAssign. So let me move this Zoom tools around. I think I want to close that. So say you're back in WebAssign and you go to, oh, where am I going? This is probably the first page you're actually going to see as a real student using the WebAssign system. Here, it says your current assignments is 2. It's referring to these 2 assignments. There's also past assignments, so you can click here to reveal them. And if life kind of got away with you, if you didn't get all these problems answered, you can always come back here and finish this out. So the way you request an extension in this class is click this button right here, request extension, when you're here under past assignments. It reveals this weird little dialog here. You can request an extension date. And I don't really have any guidelines here. I'd say just do what makes sense. Sometimes I'd say the best overall thing to do is put it 1 week out, something like that. Again, I'm not too worried about the date or the time. And you don't have to say anything at all here. I should mention that you don't need to let me know anything going on with your personal life unless you feel like it's relevant to share. Some people might just say work got, let me find the home row, work got busy, and that's good enough for me. But again, you never really have to put anything there at all. I understand that we're all busy people. It's not always easy to get these done on time, but click submit. It says here, confirmation submitted on, that's kind of weird, a huge confirmation page, looks like a tax form. Then what happens is an email gets sent to me. I'll see the extension and just click something like confirm on there, and then the extension will go through. So it could take a little bit of time to make the extension happen. You may want to plan ahead and just, if you know that you're not going to hit that homework by the due date, you need extra time, you can request an extension a little bit earlier as well. Well, any questions, folks, about getting extra time on completing homework assignments? Okay, again, one thing I need to reiterate is for our class, the homework assignment due dates are purely for pacing, nothing else. So if you come back here and request an extension, you can get full credit on this homework assignment, and there's no penalty there. And another thing I want to mention is you can request these multiple times. Maybe, for example, you're just nearly done with this section, but there's one problem that just keeps coming up. You never get it done in time. You never make it to office hours or something along those lines. If that ever happens, definitely look into avenues of office hours or click the Ask My Instructor button. But if you find that the due date went past again, just come back here, request the extension again. I promise you, it's never going to annoy me if you request an extension multiple times on a section. If you request an extension on multiple sections, that's not a big deal to me at all. Well, that's my spiel on WebAssign, studying out of the textbook and requesting extensions. I think that's totally it for my announcement so far. Any questions at all then, folks, before we get started? Okay, well, we're in section 2.4. There's only one more section, 2.5, we'll be covering in chapter 2 before we get on to the next topic, derivatives. So it's starting to all come together, but at this point in the class, I would say as a student, this is all still kind of foggy. Why do we need limits? There's not a clear answer to that just yet. We'll find that answer very soon when we're in section 3.1 of where all this mathematics is going and why we had to really worry about these kinds of topics. So here's where our note starts. We are looking at three major topics. Continuity is going to be the next section. Section 2.5. Differentiability will be chapter 3. And integrability, that'll be starting in chapter 5. So that's kind of major organization of the course. But the thing that we always have to keep reminding ourselves is every single time we define anything interesting in calculus, they are always defined in terms of a limit. So that's really the major reason we're doing all this. But we have to still say what all those terms there mean. So this is more of just a preview. Another thing to keep in mind is these limit laws, they're essentially inherited from section 2.2. Like we mentioned, the only difference is here we're taking a limit going towards a finite number. So that's the limit as x tends towards a, not an infinity or a negative infinity. Also, the limits have to exist for any one of these limit laws to actually be true. And the second remark is just a reminder that whenever this happens, this is really a limit that does not exist. Why don't we say DNE on it? The only reason we never say DNE if the limit comes out as a positive or negative infinity is because those descriptions, those infinities, tell us the way it failed to exist. It may have been blowing up towards positive infinity or shooting down towards negative infinity. But the limit doesn't, if the limit doesn't exist, if your answer is infinity, it's noteworthy that none of these limit laws actually work because these require both of those limits here and here to actually exist in the first place. So that's a weird technical issue that can come up, not in a serious way, but at least worth mentioning. So again, here's our limit laws. There's quite a lot of stuff here, and takes quite a while to get used to them. So what we'll do is just take a quick screenshot, like we did in section 2.2, and we'll cite these as we move through the notes. Cite which ones we're using and how they're being used. So in section 2.4, we're looking to do these limits more algebraically. 2.3 was all graphs like this, but we're also trying to get used to the limit laws. So we'll actually, in fact, have a couple problems like this involving just graphs. So here's how the first one goes. Oh, and before I get too far ahead, I should mention, because I forgot about it last week, I forgot to actually assign quiz number 2 last week. So if you look at the prior week, nothing is due as far as the quizzes go. This is the new one that'll be due Wednesday, September 11th. This is a problem where you're creating a graph that satisfies various limit properties, those 6 properties right here. It's very similar to a problem that we did in section 2.3. So you can take a look at that problem before going for this quiz. So sorry for the stream of thought breaking there a little bit, but I thought that was worth mentioning. Well, here's our new situation. We have 2 different functions. One of them is a f of x function. The other is the g of x function. So over here on the left, this is the entire graph for f of x, and this will be the entire graph for g of x. Using just the graphs, we're now trying to compute these types of limits, where it's not just a single function, but some combination of a function. Maybe we're adding them, subtracting them, multiplying them, dividing them, and so on. Nonetheless, we kind of know from our intuition in the prior sections, if you take that kind of limit, all you're really going to be doing is this. Use limit law number 1, which says the limit of the sum of the functions will become the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. So that's our first step, and that's limit law 1. Sorry, what was that, Carlos?
Sorry, I accidentally unmuted.
Oh, no worries at all. I sometimes forget to unmute in the first place. Any other questions, folks, with that first step? Okay, so that's our first step on that one. We use limit law 1, and now essentially the limit laws are done. Now we actually have to evaluate the limit based off the graph. And this can be tricky because this one's referring to f of x. We have to know we're just dealing with this graph alone. So if you're over here for f of x, as the limit of x goes to 2, go to 1, 2 on the x-axis. We have an open dot right here. That just means f of 2 is undefined. But that's irrelevant to the limit. All we care about is what is the height of the curve as you get closer and closer to 2 from either side. If you're coming in from the right, it looks like it's getting closer and closer to -1, and same from the left. So we get a -1 on this one. In blue, just convey it came from the f of x function. Then we just do it again over here. Anyone see what the limit should be for the g of x function? Yep, absolutely, Emily. This one would come out as a 2. It's a little bit nicer to see because there's nothing crazy going on in the graph other than it has a sharp point right here. But coming in from the left, the height approaches 2. Coming in from the right-hand side, the height is also 2. So that's a result of that limit. And now we're essentially done. Notice that we had to write the limit statement on the first step right here. But once we actually get the numbers, we drop the limit statement. Here, we just do the computation, and we can say, when you add up both functions and take the limit as x approaches 2, the result is now 1. So that's the name of the game, and that's how each one of these are going to go. I seem to have broken some of my formatting here. Let me see if I can fix that. Oh dear, I broke it in a bad way. So I have one limit over here. Oh geez. Let me see if I can fix this really quick. I think I have a issue on my formatting. tables are great until you realize that you can't just paste anything anywhere. So what's going on with this table? I should have pasted down there. That would have worked out. Let's consider this like a mental break while I figure out what I did here on the notes. And that's pretty much unreadable. I had a lot more limits than I realized. So the steps were lim x approaches 2 of the f of x function plus the limit as x approaches 2 of the g of x function. It's like a really fast recap. And then on the f of x function, limit approached -1. So here's the -1. Plus for the g of x function, the limit approached 2. Okay, I think we finally got it. And the value was 1. You know, that would have helped me if I put this in and just left it in the notes. Let's go with inside vertical bars. Okay, that'll help me out for the next one. Well, any questions at all, folks, with the first evaluation? Okay, well, let's try this again. And I'm going to change my strategy here. The screenshot idea did not work with the table. Let's just instead go to our actual notes. And I'll cite these just by pulling this up. I think that'll be a little bit easier. Okay, well, one more to get, well, 5 more, but here's the next one we want to take a look at. This time we're doing a subtraction, and the next change as well is that x is tending towards 0. So we have to also watch that portion. But for as far as the limit law goes, all we're really doing here is using limit law number 2. Essentially the same as limit law 1, except if there's a minus, we split into 2 limits like before with a subtraction sign. So here's how this one will go. At the very first, we'll go limit as x approaches 0 of the f of x function minus the limit as x approaches 0 of the g of x function. And now, like before, we're just evaluating the limits purely by the graph. So as we go to 0, the height of the function for f of x is approaching height of 2 on either side. So we will get a value of 2 on this one. Then minus, as we approach 0 for g of x. This one's a little bit trickier. What would you all say is happening to that limit? Any volunteers for what should go on with this one? It's either a 2 or a 3. So that's a good response on that one. It depends, right? The limit as x approaches 0 from the left would give you the 3. From the right would give you a 1 over here. And then the situation becomes does not exist, like Jamie said. So the trouble with this one is, if you see a jump like that, we refer to that as a jump discontinuity. There's really 2 great answers. Either it's 2 or a 1, but that means the total limit is does not exist. So I'll write here, DNE. The instruction said, if the limit does not exist, explain why. Well, this one didn't exist because of the jump discontinuity. And so we can say does not exist because there is a jump in the graph of y equals g of x. So this is the whole answer here, does not exist. And that's one weird thing to watch out for. There's always going to be a problem as we head towards 0 on the graph for g of x. So anytime we have a 0, it's a does not exist. But there isn't a problem if we go towards -1, because that's just one point that got removed, not a whole graph sliding up or down, breaking in that jump. So that's how this one goes. Any questions at all, folks, with part 2 of this problem?
Just a quick question. So anytime that the limit is as x approaches 0, it's a does not exist?
Exactly. If g of x is involved and we go to 0, it will absolutely be does not exist. Yes.
Thank you.
Yep, you betcha. Emily says, in what situation does the open versus closed circle matter? It would matter if you're dealing with, say, this portion right here. Oh, didn't mean to scribble it out. I thought that was a highlighter. Let me try again. It's going to have a big impact on that. If you're evaluating an ordinary function value, now it suddenly is a big deal whether or not there's a solid dot here, or up there, or otherwise. But if you're just taking a limit, 1 point moving away, like right here, doesn't change the limit. It's this kind of breakage that will destroy the limit, make it does not exist. Does that make sense for that question so far? So Dennis says, always or for just these practice graphs right now, in regards to g of x always being does not exist at 0. Yes, we can say, let's put down a good statement on here that, oh, and I missed. Let me try circle it again. In this situation, a jump, we're later going to call this a jump discontinuity, so I'll say it here. But if you called it just a jump in these notes, that wouldn't be bad either. Let's call it a jump discontinuity. Always causes the, let's call it the double side limit. These are the ones we're taking a look at. We're not heading towards 0 from the left, which is single-sided, or 0 from the right, which is single-sided. So it'll always cause the double-sided. Limits to not exist. So yes, that is absolutely correct, Anna. And Cameron says, so the answer is 2, or is there no answer? The answer on this one is just does not exist. So just to convey that, let me see if I can circle this one a little bit better. Getting the 2 right here wasn't so much of an issue, but we just noticed we got stuck on the next portion. The total answer on this, just to convey it better, is the does not exist, an explanation down below. So that's a really great question as well. Essentially, what this is saying is, if one part of this expression here resulted in a does not exist, then the whole equation is ruined. The entire expression is now does not exist. Any other questions or comments so far? Okay, well, let's try this again. Same idea, 2 functions, and this time we have the product of 2 functions, f of x times g of x. And the good news is there's absolutely a limit law from that one. Let me see if I can pull that up. We're looking now at limit law number 4. The limit as x tends towards a of f of x times g of x can be broken up in this way. Notice the tiny little multiplication sign there by the red dot. It's saying the limit of a multiple of, let me say this again, but in practical terms, my finger would be right about here, tracing along the limit of 2 functions multiplying is the limit of one function multiplied by the limit of another function is the result here. So putting into practice, my first step on this would be to say this turns into the limit x tends towards -1 of f of x. Because the limit operator is kind of a strange one, I probably would put that multiplication sign there just to be explicit. We are multiplying the results. Multiply by the limit as x tends towards -1 of g of x. And now we just have 2 fast limits to calculate. Any volunteers for what should happen for f of x and the limit? Oh, lots of responses. Folks are saying this should be a 1, and absolutely, good call. It is kind of tricky because, in all honesty, it's tempting to say 3, but that's the function value. The limit is what you're getting close to as you approach -1 from either side. From the left, it's approaching -1, and from the right, it's going down, 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 towards +1, as x tends towards -1. So the limit here is a positive 1 from right here on the graph. Then now at g of x, let's see, we're heading towards -1. We'd be right here. And there's no problems on the curve. It's a nice, clean curve with no breaks. So this one would be a limit of 2. So now we have a 1 plus 2. And so the total limit is 3 on this one. So that's 3 limits. Just a few more to go, and we'll be on our way with this problem. Let me take a screenshot of this so we can go down to the next ones. But any questions, folks, so far? Oh, you're right. I have a multiplication here, but it looks like that was just a copy error. Thanks for spotting that, Emily. The math here is still as it was all before. Multiplication wouldn't change. Let me put here times, and I think that deserves some highlighting at that point. Sorry for that weird error. That definitely affects the limit. This came out as a 2 in actuality. Thanks for fact checking that one there. Any other questions or comments so far? Okay, well, let's take a look at the next 3. So here are our functions. Let me see if I can make this table look similar.
Actually, I do have a really quick question.
Sure.
Can you explain one more time why on the f of x you would do 1 instead of 3?
Yeah, absolutely. So what's happening on f of x is, let me get a different color pen. It's about that spot right there. When it says the limit as x tends towards 1, or excuse me, -1, you're trying to get to this part on the x-axis, and it's like you're constrained. You have to be on the graph here and here, because the value doesn't actually matter when you're at -1. The only things that affect the limit is what happens as you get closer and closer to -1. So the parts of the curve that are relevant are right around here, shaded in purple. And right around those locations, the heights are getting closer and closer to a height of 1. But it is true to say f of -1 is 3. That's referring to the function value that actually exists there. But again, what's tricky is this part right here. Let's leave this actually on the notes. The limit as x tends towards -1 of f of x is the value it's getting closer and closer to, +1. That's a very tricky distinction. I think that's what makes limits the trickiest. It's the reason why we're looking at all these kind of graphs, to just get a feel for that difference right there. But does that help out with that question so far?
Yes, thank you.
Yep, absolutely. Any other questions at the moment, folks? Oh, sorry, I didn't mean to go to this. Let me just cancel that out. Trying to click on the chat. It's being a little touchy. There we go. Cameron says, not to be picky, but I think that 2 is actually a 3 and y equals g of x. Oh, geez, let me take a look. What were we looking at for that one, Cameron? Was it this last problem right here? Gotcha. Honestly, sometimes I personally have trouble reading these axes, because it'd be nice if they made this a bold line and this a bold line, so it could just stand out a little bit better. So I personally sometimes get the wrong number on these. And let me take a look. This was the limit as x tends towards -1 on g of x. So we would be right over here. And it looks like this one would come out as a 2. But again, it's a matter of seeing the axes right. Does that make sense so far, Cameron? Awesome. Other questions so far? Okay, well, I think these ones are kind of tricky in their own right. And we have 3 more just because, I mean, more practice is better for this kind of stuff. It is weird math at first when you see it the first time. So 3 more limits. Here's our 2 functions. And for this one, we're dividing the function. But you might have noticed the pattern already. Let's actually just run through what we think we're going to do, and then we'll see if we're right by looking at the limit laws. I mean, so far, what we've been doing is if we're adding the functions, we add up the limits of the functions, or subtract the limits of the functions in this case, or multiply them. So it stands to reason that if this pattern were to continue, this should be limit as x approaches 3 of f of x divided by the limit as x approaches 3 of g of x, and double checking the limit laws. Say if this was a real exam, I'd probably just take a look and say, yeah, that looks like this is legitimate. The only thing that we have to watch out for is if the limit of g of x does become 0, we would be dividing by 0 here. But that's how the limit law starts. Then looking at the functions, well, we're heading towards 3. So we're here and here on both of those functions. There's continuity in this case. There's no break, no open circles, no jumps. So in the numerator, the limit would be 2. And then at the denominator, we in fact do have a problem. The limit of the denominator is going to be 0, providing a 0 in the denominator right here. And this automatically gives us a does not exist. So we actually did hit this special case. This limit would be legitimate, it'd be correct, and we could calculate it if the limit of the denominator did not equal 0. So here we get to say does not exist, since the limit as x approaches 3 of g of x is 0, implying we're dividing by 0 in the denominator when we attempt to evaluate the limit. So that one's almost a freebie if we saw the problem, division by 0 because of that part of the graph. Does that make sense to folks on that one there? Okay, well, it gets weirder and weirder as we go. There's a couple extra trick problems on this one. Starting with this one right here, notice there's no f of x, g of x, there's just a f of x and just some other extraneous function. But nonetheless, notice that those are being multiplied. X squared is multiplying a f of x function, so we can go here to limit law number 4 and still split into two limits in that kind of way. The first one where the red dot is, we'll just say limit as x approaches 2 coming from here. We'll plug an x squared where the f of x is. Then just a f of x here. So splitting this off, let's still think in terms of blue and green, just for the pattern. This turns into the limit as x approaches 2 of x squared. Then it multiplies the limit as x approaches 2 of f of x. So that's our first limit law. We just had multiplying functions. So now we're multiplying the limits of those corresponding functions. Any questions, folks, to this stage? Okay, well, we know how to read this limit, but the one right here with the function in green, that's the tricky one here. You might have a good guess on this. If you felt, well, x squared is a graph that goes like this, there's no poles, there's no problems with continuity on this, there's no jumps or at all, you should be allowed to just put a 2 there, square it, and get a value of 4. In fact, that is true. There's a special class of functions where all you really do is take the number and plug it in. We're going to find that in these notes, what those functions are. But that's also a limit law somewhere on here. Let me see if I can find it. It's limit law number 9. It says the limit as x approaches a of a function x to the power of n. Here it's x to the power of 2, so the n is 2 this time. Well, you just take a, you plug it in, raise it to the corresponding power. So if we use limit law number 9 verbatim, it would look like this. We take the power 2 function we had. The limit as x approaches 2 goes inside. And that handles the very first limit. All we now need to do is work this one out. But I feel like this is the trickiest part of the entire problem right here. Any questions at all getting that 2 squared? Okay, going off to the f of x function, well, it says x is approaching 2, so we would be right over here at 2. There's an open dot there, but that's okay. That just means the function's undefined. Anyone see what the value should be right here based off that graph? Sorry for scrolling, just trying to find a good spot. Kiana says -1. And yeah, absolutely. Even though there's a hole right here on the left-hand side and on the right-hand side, the curve is going down, down, down towards the height of -1, like you said. That means that is the value of the limit, even though the function's undefined right at that spot when x is 2. So we take the value -1. I want to use blue just to convey where it came from. Then the whole thing is just a quick arithmetic computation, 4 by -1, giving us a result of -4 on that limit. So we did it, folks. Just one last one to go. This one is pretty tricky as well. I feel like, again, this is the trickiest one. It's good to reminder that you use the limit laws even when you know the actual function. So we knew this was x squared, coming down to that limit law. But this one's different because it's asking for a function evaluation. So when it says f of -1, we're going over here to -1. We pass through this open circle and we land right here at a height of 3. So f of -1 would turn into a 3 to start. Next, we take the limit of g of x as x heads towards -1. Let's see. Notice we didn't use a limit law because, well, there was just a single function right here in the limit, so no limit law was required. So we just go to -1. We have a height of 2, and that satisfies the limit. The result on this one would be a 5. So that's how to calculate limits, applying the limit laws as you see them through two different graphs. Any questions at all, folks, on getting through these problems?
So when you're dividing, you can do it with any number just as long as it's not 0.
Exactly. So if that limit came out to a 2, we would have had a limit that existed.
Okay.
Eli says, sorry, we used 3 instead of a 1 because of what again? Oh, it's because it was just the function f. There was no limit in front of it, no instructions where x is heading towards. If it's just a function with a number as its input, then we just pull the output from the graph using the solid dot. Does that make sense there, Emily? Awesome. Any other questions so far, folks, with these? Okay, well, notice that some of these limits involve taking a number and just plugging it in. We'd like to do more of that kind of stuff, and that's where the notes are heading towards now. That property that we used is referred to as a direct substitution property. That makes it sound important. It applies to two classes of functions, the polynomial function and the rational function, as long as your input A, the value x is heading towards in the limit, coming from right here, is actually inside the domain. If it's in the domain, then all you do is you take your A right here, plug it inside the function, and that gives you the f of A. That's exactly what we did right here. We took the limit as x approached 2 of x squared. That is a polynomial function of degree 2. Just plug the 2 inside and we cranked it out. So we want to do a little bit more of those. But I felt like before we use this property a whole bunch, example 2, not a direct question you'll see in the exams or the quiz, but it's still useful because we did need to know what are the polynomial functions. What do they look like? Sorry for the scrolling. And that's what part A is all about. So for examples of polynomial functions, they could be things like this. F of x equals -3x cubed plus 6x squared plus 7. Or it could be a function as simple as, let's use just a different letter, g of x equals 3x minus 8. So up here, the first one, this is a degree 3 polynomial function because that's the highest power that appeared. This one's considered degree 1 since the power that appears at highest is power 1 right here. And you can get even weirder polynomial functions. For example, h of x could be 10. It's a bona fide polynomial function, and this would just be referred to as having degree 0. So for every single one of those functions, if we ever take a limit, all we're doing is plugging the number anywhere x occurred. We'll practice some of those next after the algebra review. But any questions, folks, on the polynomials? Okay, it's a fantastic property because it takes something that's mysterious, evaluating a limit, and it just makes it familiar. You're just plugging in a number in this kind of way. So for the other kinds of functions, the so-called rational functions, here's where our examples will be, right down below here. So a typical rational function could be something like this. F of x equals 1 over x. It's rational in the sense that it's a ratio of a polynomial, a constant polynomial degree 0, and another polynomial, this one is linear, degree 1. So that's what makes it rational. Another example might be g of x equals x squared plus 6x plus 8 divided by x minus 3. This is an interesting rational function. It has a degree 2 polynomial in the numerator, degree polynomial 1 in the denominator. But as long as a fraction occurs, we consider it a rational function. Any questions, folks, with our preview of functions here? Okay, well, again, the major reason we care about these things is the direct substitution property is an extremely powerful way to evaluate limits. We just have to know when does it actually apply. It applies to the polynomials or the rationals. Let's do a quick example right here just to see what it might look like. After I click on the cursor tool, okay, here's the copy of the actual statement of the direct substitution property. And if we took the limit as x approaches 0 of x squared plus 6x plus 8 divided by x minus 3, that could be a pretty hard limit where you don't have a graph. And we don't want to do tables of computations like we did at the end of section 2.3. That's pretty tedious to get through. But once we realize this is a rational function, all we need is the value of a, that's this value, to be in the domain of that rational function. It is. The only thing not in the domain is 3. 3 causes division by 0. So that number there is in the domain. This is what direct substitution looks like. The whole limit becomes equal to 0 squared plus 6 times 0 plus 8 divided by 0 minus 3. So we get to negative 8/3. So that's as fast as it can be if we have the right kind of function. Any questions, folks, with that quick demonstration there of the property? Okay, now the trouble is, what happens when a is not in the domain? That's where taking a limit is a little bit more difficult, but it just becomes a preview or a review of algebraic techniques to change the function until the number a is in the domain. And we'll show how to do that carefully on the next problems in the notes. So here's the restatement of the direct substitution property. So we're very interested in polynomial functions or rational functions. And here, this is where the direct substitution property is going to work out pretty nicely. Once we go over here to example 4, or this is example 5, sorry for the numbering, counting was hard, I suppose. This is when the direct substitution property fails, and we'll show how to carefully navigate through these examples. But first, these are kind of the fun limits. This function right here is not so bad. It's rational, degree 2 in the numerator, degree 2 in the denominator. If x is approaching 0 in the limit, Then all we have to do is write out that this is equal to, and maybe first, just for the sake of the notes, let's say here that this is a rational function. So this would turn into, everywhere I see an x, I'm just putting in an open parenthesis. So we had 4 positions for x. Here's those 4 open parentheses. Take the value in the limit. Let's see, we'll go with that right there. Well, maybe that might not be too easy to read. Let's just use yellow highlighting. We'll take that value. Direct substitution now looks like this. Whatever the limit is heading towards, 0 just had to be in the domain. How can you check? Your denominator just has to be non-zero. So that means we're in great shape. We have a value of 0 that's in the domain. And now this whole thing becomes 0 in the numerator divided by -1 in the denominator. This is okay. The one thing we're avoiding is a 0 in the denominator. It tells us the overall limit is just a 0. So no fancy computations. All we literally had to do is take the value and plug it right in. Any questions, folks, on getting through that one? Okay, these are like some of the fastest kind of limits that we've seen all day. And now this is where it kind of goes a little bit awry. Limit as x approaches -3 of 5 times a square root function. Trouble with that is the entire function here, due to the square root, this is not a polynomial. So we need to be a little bit clever when we go through this. What we now need to do is write out or take a look at what we have available to us in the limit laws. So looking through here, limit law 9, 10 doesn't help us, but limit law 11 absolutely does. Let's take a screenshot of this one. For this to work, n has to be a positive integer, and n must be even. If it's even, rather, we have to have a positive function. Here, the index is 2 if it's an ordinary square root, so it does qualify for limit law number 11. So let's put down the limit law here, just to say what we're about to do on it. I think that's a good one to directly cite. So what happens? Well, the limit's on the outside, and then it goes inside first. Well, there's a little bit more going on. We also want to use, let's see, we have a constant times a function. Probably limit law number 3 should be thought of as well. That'd be the first limit law to use on this one. And this is essentially how you might be doing this on, say, an exam or the homework. Taking a screenshot and plug it in is kind of like looking at the notes provided on the exam for what limit law you're about to use. So where limit law 3 is, this would turn into 5. The 5 is playing the role of c on this one, times the limit as x approaches -3 of the square root function, x squared minus 2x. So that's limit law number 3 in action. Now, this is the interesting part. Limit law number 11 says if you have the limit of a root function, the limit operator goes inside the root. So this turns into 5 times the square root of the limit as x approaches -3 of the function x squared minus 2x. So that's how that limit law goes. Next, once we get here, this is where the mathematical miracle occurs. We now can use direct substitution because we, in fact, have a polynomial. So we can use this property here. And just to convey it on the notes, that right there is a polynomial. I'll shorten it to poly since that's a really long mathematical word. So taking the limit of that polynomial just means -3 goes in the positions where you see x. So this is now equal to 5 times the square root. It's x squared minus 2 times x. The value of x is -3. which came from right here on the limit. Now from here on out, it's just simplifying this, getting through the arithmetic. And I already made a mistake. I forgot the 5. Okay, second try. This is 9 plus 6 altogether. So our answer becomes 5 times the square root of 15. And we did it, folks. That's a pretty challenging limit on face value. But you'll notice what essentially happened was -3 just went here, here, and we took the root. Any questions at all on getting through example 3? Okay, well, again, these are kind of the nice limits because these values 0, -3, they were in the domains of the functions that we were interested in. So we have to know, what do we do when it's not in the domain? And that's where we have some pretty interesting tools to help us out. First, definition 1 is just a restatement of what we mean by a limit. It says f is defined with x is near the number a, so the function values of f of x have to exist around a. Then the limit is L, as long as the height of the function gets closer and closer to L as x approaches a from either side. So that's a pretty powerful definition. And below it, if I can bring that up, this is the big theorem that allows us to calculate the limits when direct substitution doesn't work at the start. It says if f of x is actually equal to g of x, except for when x equals the value of a, same value that's being mentioned up here, then that doesn't matter. Just like when we have an open circle in the graph, everything around it is what matters. So if the functions are equal, then we'll say the limits are equal as well. And let's take a look at a screenshot from back in the day. It already feels like a little while ago. That's pretty much what this example 2 is all about from the section 2.3 notes. So let's plug that into where we are currently. And this is that example that uses the theorem below. Let me pull that up a little bit more. Taking the limit of this function as x approaches 1, so all these are as x approaches 1, is pretty tricky if you didn't have the graph, so let's hide the graph. And let's do it from scratch. The limit as x approaches 1 of x squared minus 1 divided by x minus 1. Let me get my color coding set up again. So in the theorem below, we have a couple functions. And this is the function in blue, x squared minus 1 divided by x minus 1. It's no good to us. We can't use the direct substitution property on this at all, even though it's rational, because if you took 1 and plug it in, you divide by 0. So 1's not even in the domain of this thing. We need a new function. In other words, we need to find the function g of x that's going to help us out. So we take this to the limit as x approaches 1, and now we have to dig deep and just do something algebraically. If you saw x squared minus 1, a good thought is that factors as a difference of squares. This is x plus 1 times x minus 1, still divided by x minus 1. And now if we cancel, which we always do algebraically in this kind of context, we get this function. Limit as x approaches 1 of just x plus 1. That's actually a different function. You can see from the graphs, there is a big difference. One had a discontinuity, one didn't. But when we take the limit as x tends towards 1, we don't actually care about what happens at 1. We just care about what happens on either side. So even though there's a difference on the graph at one spot, it's irrelevant. We have a new function h of x that's going to go here. The functions are almost the same, except they have a disagreement right when x is 1. But that's okay. We can still take the limit if there's only one spot of where the functions differ. So back over here, now we have a polynomial function, so it's simplified a lot. Direct substitution works, and we get 1 plus 1 for a total limit of 2 on this one. So that theorem is fantastic. It says if you do weird cancellations and change the function to something else, it's allowed. We're trying to reduce the functions, get them to a point where direct substitution actually works. Well, any questions, folks, with example 4? Okay, I said example 4 because I'm looking at how I did this, and we essentially solved example 4 right here, but let's just write it out so it's apparent in the notes. We have more interesting examples coming up next, but the strategy was to just factor as x plus 1 times x minus 1, simplify it, then here, all we did is take the 1, directly substitute it into the value of x, and we got our answer. Sorry for doing it twice. I forgot that was a problem right down below, but it makes the notes readable. So this is kind of the idea of what we're getting into on example 5 finally. We want to do something algebraically to the function to get it to the point where the limit would exist. So here's our next bit of problems. Any last questions, folks, before we try out the problems on example 5? Okay, the theorem is a kind of a vague statement, but essentially, again, all it's saying is cancellations are actually allowed when you go to take the limits. So let's see how these go in practice. And when I look at this, I would probably do a really quick check, grab a calculator. I don't know what's going to happen with that -3 down here and that denominator, so let's just compute it. We would have a -3 squared minus a -3 minus 12. And that equals 0 is a problem. That means we can't directly substitute it. The limit may in fact exist, but we have to see how we can get there. So next step, the idea we need on this one is we have to factor. And pretty much every one of these problems is going to have a new algebraic idea. So let's say here, requires factoring. So step 1, let's take the limit as x approaches -3. We can factor the numerator in a nice way. This just has a greatest common factor of x. So we'll factor out x, leave behind x plus 3. Factoring the denominator is trickier, but there is a big hint on this. If you saw an x plus 3 in the numerator, there's probably an x plus 3 in the denominator. So let me plug it in, hope for the best. That x looks suspicious. Let's fix that. So here's x plus 3. We're factoring x squared minus x minus 12. So I would definitely want an x minus. And to get the 12, we just need a 4 there. Thanks. Yeah, absolutely, Jamie. An x minus 4 would do the job. So this factoring is kind of nice in a certain way. It's not as bad as factoring you might have done in algebra classes, because, again, there's usually a hint. If you saw x plus 3 above, it's probably going to be below. So this allows a cancellation. And that's the entire content of the theorem above. It just says you are allowed to make that cancellation happen. Then we transfer this to a new limit. But here's where the remark that you might have noticed in other places of the notes come into effect. When we write out the limit statements, we have to use correct limit notation, which means we do have to copy this. And I mean, if you did forget to copy that on a quiz or an exam, you'd only lose points once. And with a comment, it needs to go there for correct limit notation. It would copy in again over here. The limit as x approaches -3 of x divided by x minus 4. But this is the last time you would copy it, because the next step is just direct substitution. Notice that this rational function, it is not the same as the original one over here on the left, but that's okay. They only differ on one point. They agree everywhere except when x is equal to -3. That means we can just use direct substitution here and get -3 divided by -3 minus 4. So this looks like a -3 divide by -7 for a value of 3 sevens altogether. We did, folks. That's the way to get the limit on this kind of thing. Any questions at all with this example? Okay, when you go to do these on WebAssign, you can pretty much come back to example 5 to get some ideas on what is the algebraic technique I'm looking at, how should I approach it. If you're not too sure how to start it, don't hesitate to click the Ask My Instructor button. I'll be happy to give some hints. So same instructions, all we're doing is evaluating the limit. And here's the next one. It looks kind of weird because we have h's in place of x, but just think of your h as an x and you're in good shape. It says root 1 plus h minus 1 divided by h. And honestly, this one's a pretty tricky one to start, but here's a good formula that gets us there. This one requires a conjugate. And when a conjugate comes into play, we always have this formula. A plus b times a minus b becomes a squared minus b squared. In fact, we used this formula once already. That's how we factored on this one. This is the difference of squares. It's just involving that formula right there. So we need to take and find the conjugate of this thing. And it starts off by going the limit as h goes to 0. It's a little bit of copying to start out. Root 1 plus h minus 1 divide by h. And right here, we have to multiply by the conjugate. Anyone recall what that would look like? What would go in the numerator?
The square root of 1 minus h plus 1.
Exactly, good call. So it would go root 1 plus h plus 1. And pretty much this is the name of the game. If you need a conjugate, as we do here, you're essentially copying everything you see, except you're flipping the sign as you did. Then we just do it again in the denominator, exact same quantity, 1 plus h plus 1. And if there had been a minus here, we would have come over here. Excuse me, let me try again. There is a minus. If there was a plus here, we'd have come over here and done a minus. So the best way to mention this is just change the sign. Now the algebra looks pretty rough because in the numerator, we actually need to FOIL it. So this will turn into the limit as h goes to 0, but it's not as bad as it seems. Let me get some arrows going here, temporary arrows. Well, what's a good color? Let's go with that. First, when you multiply here to here, it's a root times a root, and you would just get the thing inside, the radicand, 1 plus h. So that's kind of nice. Next interesting thing is, when foiling it, here to here, you have root 1 plus h, and then here to here, you have negative root 1 plus h. So that's a clean cancellation. Notice that's what's happening here, just two terms. The middle term just cancels when you multiply that out. So the last thing to actually multiply is really just here to here. That'll be a -1 times a +1, so we just get a -1. So it looks ugly, but essentially following those arrows, that's the way these multiply out. Because it's a conjugate pair, the one in purple, the one in black, you should expect a massive simplification and a really fast multiplication. Does that make sense to folks on multiplying through the numerator? Okay, as far as the denominator goes, it's actually a good call to leave it in factored form. So I would write this one as h multiplying root 1 plus h plus 1. So that's our limit to take a look at. But there's even more cancellations. Notice the plus 1 minus 1 cancel off. Let me write it this way just so the notes don't get too busy. So this turns into the limit as h goes to 0 of just h in the numerator. Denominator is h times root 1 plus h plus 1. And now here's a new cancellation. And here's again the value of why we actually didn't multiply h through this group right here. Left in that format with h factored out, it's more clear that this and this become a cancellation. And actually, that's really great for us because notice, the only reason we required the conjugate and we took this step is because h going to 0 meant you couldn't plug h 0 right there. Direct substitution was off the table. We couldn't do it at this step. Not sure what I did there. Let me fix that. We couldn't do it at this step because h is alive. We couldn't do it at this step. But now at that stage, when we canceled h out, we changed the function, but now direct substitution will work for us. So let's take a look at those last steps. This is now limit as h goes to 0 of 1 divided by the root 1 plus h plus 1. In direct substitution, the limit affects the root, but it goes inside the root. And in practice, we usually just take this step. That 0 there becomes a 0 right here. And we have 1 over the root of 1 plus 0 plus 1. Now it's all algebra from here. It's 1 over. This is just the square root of 1. Square root of 1 is just a 1. So 1 plus 1. And now it tells us the end result on this whole limit is nothing but a 1/2. What we did, folks, idea for this one was just requiring a conjugate. Any questions at all getting through this problem? Okay, I'd say with where we're at in the notes, you could pretty much finish out section 2.4 if you want to start it a little bit early, working through the problems. You might find problems that are a little bit tricky. For example, this one we'll have to do when we come back on next Monday. It just involves expanding out the numerator and simplifying. It's not so bad. But the ones that are going to look kind of terrible are these last two. So if you leave problems like these for very last, that would kind of make sense, but you're welcome to try them early if you like. It's all about finding least common denominators or clearing denominators on this one. But those will be our last problems before we go to our exam 1. And again, next Monday, if you have further questions, we'll have an impromptu review day after we finish these notes here. Well, any last questions at all, folks, before we call it a day? Okay, and again, sorry for the cancellation of the office hours today. That really kind of sucks. I have a mandatory meeting today from 3:30 to 5. That's why I'm not in my basement. So let me see if I can show you. I'm in an actual classroom here in Idaho Falls campus. So I have to get going, but I can still take a few questions before my 3:30 meeting. But if you don't have any questions, have a great weekend, folks. Kind of weird working only one day of the week. Sorry, go ahead.
I have one quick one. Just back like at the very beginning.
Yeah.
It was example 5 under, that first set we did.
This one right here?
Yeah, could you just explain why where you got 2 squared? I kind of got distracted there, and I've been wondering how we got 2.
Gotcha. This one was from a particular limit law. We use this limit law number 9 right here in the bottom.
Okay.
So the x to the power of n matches up with x squared. We just took our value in the limit 2 and plugged it in.
Okay, that makes sense. Thank you.
Yep, you betcha. Thanks for asking about that.
Okay, I have a quick question just about the problem we just did.
Sure, let me zoom down to that. Okay.
So why did you put the same thing in the denominator that we were like dividing by?
Oh, that's a really good question. I usually make a comment about that, but I think I just totally forgot. The reason we had to put the same above and below is because that whole thing is just a really fancy 1. So we're multiplying the original function right here by 1, which means we're not really changing it. So algebraically, this big mess is the same as that up there.
Oh, okay. So like if we put it as 1, would that be okay? Or would you just suggest just doing it like that?
You could make it a 1 as your first step, but then you eventually have to write in this way to start working through the algebraic parts of it.
Okay. Okay. I felt like I need to just practice this one, and then if I have more questions, I'll let you know.
Sounds good.
Okay, thank you.
You betcha.
Can you explain on that same problem? You had like the temporary arrows when you were foiling, and you lost me there. How like there was a cancellation.
Oh yeah,
insert spot.
absolutely. So the tracking those arrows, it went here to start.
So that's like
That
the
was
entire square root of 1 plus h multiplied by the entire square root of 1 plus h.
exactly. And if you take a root times the same root, you just get what's inside that 1 plus h.
Okay.
Then the next arrow went here to here. This was just a 1 times root 1 plus h. So we get root 1 plus h on that one.
Okay.
Then it gets exciting when we do the last bit. Now we're taking -1, multiply root 1 plus h, just becomes negative root 1 plus h. And last arrow, it's -1 times a +1, so
Oh.
-1. And the cool thing about conjugates is the root portions, they always cancel out. So that's how we got down to here, 1 plus h minus 1.
Gotcha. Okay, thank you.
Yep, absolutely.